We've been talking about power spectral densities of random processes. Um, Here's the notation for power spectral density. Here again is the autocorrelation function. And we've already been through a couple of examples of kind of how to go back and forth, or if you're given the PST, how to get the autocorrelation function. Um, Here's maybe what a power spectral density might look like and their associated autocorrelation functions. Um, Here was an example we went through where we're given this power spectral density, and we ultimately came up with the autocorrelation function that was in a previous video. Um, we did this guy where we had to first find the PSD and then find the autocorrelation function. But here's another example, and where we'll use partial fraction expansion. If you're familiar with this, I'll do this example pretty quickly. If you're not familiar with it, don't worry about it. You need to brush up on partial fraction expansion. I cover that in my NMath A course, where we talk Laplace transforms. Let's say you're given this power spectral density and find the autocorrelation function. We can use partial fraction expansion, that's PFE. One difference is we're going to treat omega squared like we treated S when we talk Laplace transforms. We're still going to need a Fourier transform table to find the individual pieces. And by the way, a physically realizable power spectral density has to be an even function of omega, of frequency. So you're only going to see even powers of omega. Anyway, if you compare that denominator to this form in the Fourier table, that's that kind of factor. Omega squared plus a squared, or omega squared plus 4 here and a 1 here. So we have this, and we're going to use partial fraction expansion. And remember, that means you put a constant, you break up the denominator. And treating the omega squared like S, these are just real poles, real roots of the denominator. So you just put a constant up in the numerator and break up that denominator like this. And then since these would be simple real roots, we can use the cover-up method. So find A, that's omega squared plus 1. We cover up that term and replace this omega squared with whatever makes this 0, which would be minus 1. So we have a 4 minus 1 plus 4. That's 4/3. And B, we cover up this term, omega squared plus 4, and replace this omega squared with minus 4. So we have 4 over minus 4 plus 1, or minus 4/3. So there's what it is, but we need to match the tables. So up in the numerator, you need to twice whatever the square root of this guy is. And then we need, so for this guy, we have a 1, so we're going to need a 2 up here. So to make up for it, we divide by 2. And for this guy, let's see, it's a 4. So we need, the square root of 4 is 2. We need a 2 times 2 up here, so we need to divide by 4. And there is our autocorrelation function. We're using partial fraction expansion. Okay, the second thing I want to do in this video is introduce white noise. It's called white because its frequency spectrum is flat over all frequencies, plus and minus infinity. Its autocorrelation function is a Dirac delta function. Let's see, what's a few things? Remember, the power of a process is the area under the spectral density curve. Well, in this case, that would be infinite. It goes on to infinity. The area under that curve is infinity. So it's not a physically realizable process. There's infinite variance or power because of this impulse. Let's see. It's mathematically convenient, even though it's physically unrealizable, but it's mathematically convenient. That's why it's used a lot. And you'll notice the autocorrelation function is zero as tau goes to infinity. Make it zero as soon as you get away from zero. And there's no Dirac spike in the spectral densities. That means it's zero mean. So white noise means zero mean. It doesn't necessarily have to be Gaussian, but a lot of times it's implied when somebody says white noise, they really mean Gaussian white noise. But technically, it doesn't have to be Gaussian. Band limited white noise just means it's flat over some frequency band. Kind of what happens is if it's like this, but what you're interested in is much narrower than that band, model it as white noise because it's well outside your operating limits. But anyway, its PSD would look like this, a pulse in the frequency domain, and its autocorrelation function would be the inverse of a pulse in the frequency domain is a sync function in the time domain or the tau domain. This guy does have finite power. There's only so much area under this curve. The time samples are correlated except at certain frequencies. At least theoretically possible, plausible, means it's not impossible. But mathematically, it would be more complicated to deal with than pure white noise. So that's going to be the definition of white noise. Next, we're going to get into the Wiener process, which is the integral of white noise. Technically, a Wiener process is the integral of Gaussian white noise. We'll go through this, what if it's just white noise, whether it's Gaussian or not. And I'll save that for another video.